Section 5.8 is about the Fibonacci numbers. The Fibonacci numbers can be thought of as a sequence that starts out 1, 1. You have to memorize that. And then any of the next numbers are always the sum of the preceding two. So 1 plus 1 is 2, and 1 plus 2 is 3, and 2 plus 3 is 5, and 3 plus 5 is 8, and 5 and 8 is 13, and 8 and 13 is 21, and 13 and 21 is 34, and this goes on forever. So those are the Fibonacci numbers, and they don't exactly have a cult following in our world, but it sort of is. These numbers show up all over the place in nature and in art, and somewhat in music. For instance, just a few minutes ago, I just Googled pictures of Fibonacci in nature, and I didn't even click on any of the hits. I just looked at the pictures that Google sends me, and I didn't even click on those. Just a lot of pictures of this Fibonacci sequence in nature itself. So it's kind of interesting. What I'd like to do is just run through a few things that our book has to say to make sure that you understand what's going on. So it talks about adding 6 consecutive numbers in this sequence. Now you can choose any 6. Don't you choose the first 6, because I'm going to do that. So I'm going to add up the first 6. So I have 1 plus 1 is 2, plus 2 is 4, plus 3 is 7, plus 5 is 12, plus 8 is 20. And you will notice that 20 is divisible by 4. In other words, 4 divides 20. The claim is that no matter which 6 in a row you add up, it will always be divisible by 20, always. So that's kind of an interesting thing. It's not proven, but you'll be asked to check that out. And when you check it out, don't use the first 6, because I did. Another idea is that the greatest common factor of any 2 in a row is always 1. So for instance, if you choose 13 and 21 and try to find the greatest common factor between 13 and 21, the greatest common factor, or the GCD, will always be 1 between any 2 consecutive terms in this Fibonacci sequence. So notice the biggest number that divides evenly into 13 and evenly into 21 is 1, because 13 is prime and 21 is 3 times 7. And so when we go to find the common factors in 13 and 21, there aren't any. 1 divides into everything. So the greatest common factor of each of these terms is 1. That's kind of interesting. Now I'd like you to consider any 4 numbers in a row. Again, when you're asked to do this, choose a different 4 numbers. But I'm going to choose these 4 numbers right here, 2, 3, 5, and 8. And the idea here is to square each of the inside 2 numbers. So I'm going to have 3 squared and 5 squared. And then for the outside 2 numbers, multiply them. So we have 2 times 8. All right. And 2 times 8 is 16. And the difference between these two, if you write them in big, take away small order, the difference between these two, 5 squared and 3 squared, so it seems as if when you take any 4 of these Fibonacci numbers in a row, it seems as if the first times the fourth will always equal the third one squared minus the second one squared. And you're supposed to try that out on some of these problems. Why not try it out right now? Another interesting pattern in the Fibonacci sequence, there's literally dozens and dozens and dozens of patterns, is if you have 4 numbers from the Fibonacci sequence in a row, take the third one and multiply it by 2. And then subtract the next number. Do you notice anything about that number? It equals the first one. So let's try it again. Let's take these four. Let's take the third number, which is 2. Let's multiply it by 2. Always multiply by 2. Subtract the fourth number, 3, and you get the first number. When you're asked to try this, try it on different numbers besides 1, 1, 2, 3, and 5, 8, 13, 21. Here's another pattern you're asked to look at. It's a little bit different. That is, pick 3 in a row and square the middle one, and then subtract off the product of the first and the third. And here we're getting 169 minus 168, and that's 1. So let's do it again. Let's do it on these 3. We square this one and we subtract off the product of the first and the third. Square the middle, subtract the product of the first and the third of any 3 in a row. And here we're getting -1, so we don't seem like we're getting the same thing. You're asked in one of the problems to keep doing this and see what the overall idea is. One of the more important things you can do with the Fibonacci sequence is consider rectangles that have side lengths equal to consecutive numbers. So we have, for instance, 1, 1. So here's a rectangle with sides of length 1. It's called a square. Then the next 2 in a row are 1 and 2. So we have a rectangle that's 1 and 2. And then we have 2 and 3, so we have a rectangle that's 3 and 2, and 5 and 3. We have a rectangle that's 5 and 3. And as we keep on doing this forever, the ratio, the division of the sides of these, like 3 divided by 2 and 5 divided by 3, they get closer and closer and closer to a certain number. Now it starts out kind of weird. It goes 1, and then 2, and then 1.5, and then 1.666. So it seems as if it's bouncing around a little bit, but these do get closer and closer and closer to a certain number. And that certain number is called the golden ratio. And it's very famous in art in particular. And so one thing you can know about the Fibonacci sequence is as you divide a term by the one before it, and another term by the one before it, and another term by the one before it, as you keep on doing that division, you get closer and closer and closer to the golden ratio. And that golden ratio could be found pretty accurately by doing 55 divided by 34. If you wanted to find it more accurately, you could go out more places because you're getting more and more and more accurate, a more accurate estimation of the golden ratio number. And so that's kind of interesting. Here's another thing about the Fibonacci sequence. You can find it in all kinds of other places. Like I've written down the first 8 rows of Pascal's Triangle, and following the book's lead on problem 23, they suggest adding this diagonal of numbers and seeing that you get a Fibonacci number, 5. But what happens if you kind of add along the next diagonal that's parallel? So these would be the numbers right there. What happens if you add those? Well, it looks like 1 plus 4 plus 3 is 8. Is that a Fibonacci number? Well, yeah. What happens if you add the next ones, these guys? Well, 6 and 6 is 12, and 1 is 13. Maybe you could explore up here and see what happens when you add above, and maybe explore down here and see what happens when you add below. But it looks like a kind of diagonal addition, a diagonal summing on Pascal's triangle gives you those Fibonacci numbers. Now, if you're not clear where Pascal's triangle came from, note that this triangle has 1s on the outside edges, and then the rule is if you want to know what this number is, you add the 2 directly above it that it's in between. So 4 plus 1 is 5, 10 plus 10 is 20, 6 plus 15 is 21. 1 plus 6 is 7. The 1's for free. But anything in between these two 1's is the sum of the two things above it. And so Pascal's Triangle is pretty easy to fill out, and it gives you these numbers. Just a strange pattern.